Good morning, everyone. Today we will present the progress of our research work entitled Urban Wunderkammer, Physical and Digital Experience in the Historical Center of Turin. The contribution aims to illustrate a path to knowledge, communication, and accessibility of urban heritage using and applying current surveys, three-dimensional modeling, and representation tool based on AR technologies. To date, this work is still in a state of advancement from the point of view of both the consultation of historical documentation, the implementation of graphic and iconographics apparatus, and the selection and implementation of AR content. Numerous studies have focused on communicating urban heritage by exploiting AR technologies. Particularly in this, we mention IM and one work in 2024, which through photogrammetry and 3D modeling techniques capture the Semel village region that will soon be demolished due to a redevelopment project in Paiu. A 3D printed model was made of the village with AR content to archive and share people's memories. The second study by Timon and Gerald addresses the impact that augmented reality and virtual reality have on our conception, evaluation, and use of urban heritage spaces. The third instead addresses the theme of urban discovery by designing a game with an interface capable of triggering historical reflection on the user experience. In this slide, we present our workflow, the workflow adopted for this work. We started with a historical and philological study of the square, followed by the acquisition of metric data with a laser scanner, and we then develop a three-dimensional reconstruction of the building on Revit 2024, create a 1:50 scale, 50/100 scale 3D printed maquette of the plaza, and conduct AR experience test applied directly on the real model with Unity combined with Wufori engine. The ultimate goal is to be able to bring the past to life in a tangible and interactive way. As for our case study, the reference area is Piazza Quattro Marzo, located in the center of Torino, near the Duomo, the Palazzo Reale, Palazzo Madama, Via Garibaldi, Via Po, and Via Roma. This square is now the result of successive change made at the end of the 19th century through a redevelopment plan that affected several areas of the city center. The demolition of dilapidated streets and buildings led to definition of a diagonal layout that briefly joins the Duomo to Piazza delle Erbe. The facades of some restored buildings facing the new square testify to the medieval origin of these buildings complexes, built on the Roman layout that survived for nearly 2 millennia. As for the preparation of the content and the initial morphological reading of the square, some of the historical maps of the city of Turin have been consulted to date. The oldest Caracas axonometry dating from the late 16th century. The 17th century's plans drawn by military engineers, which, although drawn to study the modernization of the fortification, still provide a timely and geometrically accessible survey of the city. These maps show large-scale intervention that further deconstruct the urban layout of the whole city. The following century, the coordinated plans for the rectification of the main arteria road with the reshaping of the building fabric will permanently annul the medieval structure in many other areas of the whole center of the Via Palazzo di Città. The load-bearing skeleton of the 15th century city, of which the checkerboard imprint the Carignoni had been substantially maintained despite the practice intervention of the 16th to 18th century, was then permanently destroyed as a result of the redevelopment operation of the late 19th century. From this map, content was selected and graphical rework done. Shown here is a schematic of the plan of the urban core with the name of the main streets and squares of Turin between the Middle Age and the modern age. Also visible also visible is the subdivision into the four neighborhoods and the positioning of the Piazza Quattro Marzo area within the Porta d'Oranea district, a neighborhood that extends into the northeastern part of the medieval city, enclosed by the walls that from Porta San Michele reached through the area now by Giardini Reali to Palazzo Madama, the medieval castrum Porta Fibellone, and within the city by the streets corresponding to Via Garibaldi and Via Milano. It is the liveliest quarter of the 14th-15th century Turin. It is traversed by the northern track of the ancient Cardo Maximum, which at Porta d'Oranea joins the busy roads to Assi and Vercelli. To the south, the other Strada Pubblica terminates at the Savoia Castle and the adjacent Porta Fibellona, also an important junction point between the city and the outside. Going into the details of the area of Piazza Quattro Marzo, starting from the reconstructive studies and maps carried out by the Institute of Technical Architecture of the Polytechnic University of Turin, three-dimensional reconstruction have been made of the Carignoni and the early 18th century buildings, mostly from 3 to 6 floors above ground. Here we also see the area of Piazza Quattro Marzo and the Platea Civitas unalterated. Again, starting from the conjectural survey by the same Institute of Technical Architecture, the three-dimensional model of the late 18th century was made in order to compare it with the previous one, emphasizing the differences, and particularly visible here is the rectification of the Platea Civitas, now Piazza Palazzo di Città, and the unification of the Carignoni H and I into a single block named San Silvestro. Finally, here we see the last gutting in the late 19th century and the current configuration of the square.
Okay. Reaching the present day, the primary reference sources have been the technical map of the city of Turin and its portal, updated to 2023, and a laser scanner survey carried out by our research group also in 2023. The laser scanner survey was quick, carried out in the early morning from dawn, so as not to have many occlusion due to the venue scattered around the square, and was used as a supplementary tool to a work that takes most of its information from the technical map, which has a scale of 1 to 1000. The modeling of the actual state is the first of its operation phase. The modeling phase inside the Revit 2025 met one of the first goals of this research, which is 3D printing at a specific scale, 1 to 500. Working at urban scale on a more common software at the architectural scale requires solving some issue at all stages of the work, as now taking a building as an example. First of all, a minimum size was used for the thickness of the walls to allow for the support of the model itself and the insertion of any openings in the wall. The same logic was applied to the construction of the roof, which was created without prominent roof pitches to avoid excessive support when printing. And the creation of the roof was one of the most time-consuming operation, despite the simplicity of some Revit operation for the construction of the roof pitches in the situation where building was very regular, but this is not our case. At the modeling level, for the building of the facing square, it was decided to enrich the model by inserting the relevant doors and openings simply as undercuts, but taking the correct typologies, which we also very varied with consequent parameterization of the families, and thus the construction of simplified urban model. The next step in the work, exploiting the potential of the software, was to build various models in the same scene according to the historical phases that we'll see in a moment. The type of modeling will allow only be for masses, because we are not having the amount of information like the current state, but it become interesting to in the integration between the various models. Finally, this is the model made in Revit of the current state of the blocks gravitating around the square. As we wanted to use a limited amount of software, starting with the isolated views of city blocks, we proceeded with the export in STL format of the blocks. This export was done using the block criteria of size and to complexity to keep the next printing phase between 1 to 5 hours. Here, within the Bamboo software, the 3D printing software, some blocks directly exported from Revit are brought in the plate as an example. And here is the assembled model of the varied blocks with an overlay of laser cut boards to complete the study area. As mentioned earlier, within the same fine model, there are volumetrics model of the two specifically historical periods of the square. They will be exported with the same criteria as a limited number of software use and inserted into the various IR application.
Procedurally, it was chosen to set up the work on two scale, the first urban and the second architectural, and to realize the IR experience with Unity combined with Vuforia engine. Vuforia supports different types of 2D and 3D targets, including image targets, 3D multi-target configuration, and a form of addressable fiducial marker known as VuMark. The intent of the developed application is to overlay information about the generative geometric operation into the physical model, adopting markerless anchoring. This approach is based on a camera orientation and automatic recognition of geometric features in the real environment. In the specific case, these features are represented by the printed 3D model, which in this way acquires the dual role of a means of representation and conduit of interaction process. The application was realized using the IR camera and Vuforia model target generation. Within Unity, it is possible to upload a digital model in full-scale OBJ format. They allow the Vuforia team engine to better track the real object. It then prompts for the dimension of the model expressed in meters, and finally, the creation of the guide view occurs. An image file that traces the real 3D model from the same viewpoint from which you want it to be framed when using the app. At the end of the procedure, the model target is exported to a Unity package file to be imported into the project on Unity. In this slide, we see the test overlaid between one of the three-dimensional models, specifically the late 18th century model with the actual model. The same procedures was adopted for the architectural scale. From the data obtained from the studio by the Polytechnic University of Turin in 1993, buildings blocks have been identified and information is being organized regarding epoch of construction, few concerning building renovation intervention, or building characteristics. Here we see an example of content realization from documentation and related AR application test. In conclusion, the intent of this work is to build a tool, a graphical interface that allows the user to visualize how certain portion of urban fabric have changed over time by bringing together static content as historical image, archival documents, and dynamic contents, with the hope that such technological tool will facilitate the dissemination of information, providing a quick, simple, and new approach to knowledge, while being being careful, however, of the risk associated with the trivialization of the visitor experience and the disconnection from urban reality and cultural heritage itself in spatio-temporal terms. Thank you for the attention.